Today's lecture is all about one sorting algorithm called quicksort. That's named because it is pretty fast in practice. Quicksort, like merge sort, is a recursive divide and conquer algorithm. But the way it does divide and conquer is different than merge sort. So with merge sort, dividing is simple. You just chop the array into two arrays, and merging is where you do all the work. In quicksort, it's the other way around. You do all the work when you're dividing, and then merging is just trivially concatenating two lists together. Quicksort is the fastest known comparison-based sort for arrays. Several qualifiers. We will actually learn several sorting algorithms that are not comparison-based and are sometimes even faster. But quicksort is certainly the most used sorting algorithm in the world. When I say for arrays, that's another qualifier. For linked lists, merge sort is probably a little faster. But it depends on exactly how you code them. But in arrays, quicksort clearly comes out the winner in practice, because the constant factor hidden inside the big O notation is smaller than it is for merge sort. So now that I've said that it's the fastest comparison-based sort for arrays, it might sound contradictory when I tell you that its running time is actually theta n squared in the worst case. But if you implement it cleverly, then n squared hardly ever happens. Instead, if you practice it, virtually always runs in n log n time. With a smaller constant hidden in the big O notation than for merge sort or for heap sort. Though again, this is if you implement it right. There are lots of ways to implement it wrong. So the idea of quicksort is this. We're given an unsorted list of items to sort. We're going to pick one item out of that list that's special. We're going to call it the pivot. The pivot is going to be used to partition the array into two separate arrays. We're going to make one pile over here of items that are less than the pivot, and another pile over here of items that are bigger than the pivot. Then we're going to sort those two stacks recursively, and then we're going to just glue them together with the pivot in the middle. So that's the short version of the algorithm. There's a little more detail. Start with a list, call it I, of n input items that we want to sort. And then we choose a pivot item. Call it V from the list. And the way that we choose that pivot item is important, but it's also complicated, so I'm going to put it off for now and just describe the basic algorithm. And we will come back to this issue of how you choose a pivot effectively. So once we've chosen a pivot, however we do that, we then partition our list into two unsorted arrays, two unsorted lists, which I will call I1 and I2. But unlike merge sort, we don't do it just by cutting the array in half in the middle. We actually do a little comparisons. So I1 is going to contain all of the keys smaller than the pivots. And I2 is all the ones that are about which list to put them in because it's going to differ for different implementations of quicksort. We're going to do one thing when we quicksort lists. We're going to do another thing when we quicksort arrays. So that's a question that I'll resolve on a case-by-case basis later on. And it's important, though, that however you put those items, the pivot V itself, there has to be at least one item that does not go into either list. Otherwise, it's possible you might wind up in an infinite loop and your quicksort will never finish. So those are the rules for partitioning. Once you've partitioned, then the rest is easy because you just call yourself recursively. So sort I1 recursively. And the result of the recursive call is a sorted list. Call it S1. And you sort I2 the same way, recursively. And once we've got these two sorted lists, we just concatenate them together. With V in the middle. And that gives us our final answer. So are there any questions about this other than how you choose a pivot, which we'll see in detail later? Yes?
So it's converted that there's actually a lot of different little views that end up like this. You know what I mean? Instead of getting it like that, like 4, 5, 6, 7.
Well, yeah. So you're going to split up a list into two lists, and then those lists are going to each get split up into two lists, and those lists will each get split up into two lists, just like with merge sort. So you remember the recursion tree I drew for merge sort last lecture? At the end of the lecture. Same thing's going to happen here. Other questions? I'll draw some trees shortly, and you'll see that happening. Actually, well, I'll draw some trees now, and you'll see that happening. So the recursion, by the way, bottoms out when you hit a sublist of size 0 or 1. And then there's nothing left to be done to sort a list of size 0 or 1. Now, how long does quicksort take? The best way to address that question is to look at quicksorting several arrays. So let's try one. Let's try, here will be an array of 7 numbers. Sort those. I need to choose a pivot somehow, so let's try out a simple rule. The rule will be the pivot is always the first item in the list I want to sort. Okay? So with that rule, I start off by choosing the pivot 4. And so what we do is we go through the list, and any item less than 4 goes into a list on the left. So we scan through this list from left to right, and as we go, we either put the number into a list on the left or a list on the right. So pivot 4 stays out of the list, 7 goes into the right list, 1 goes into the left list, 5 goes into the right list, 9 goes into the right list, 3 goes into the left list, and 0 goes into the left list. So there's our partition. And now we're going to sort these two arrays recursively. Later on, when we're done sorting those arrays recursively, we're going to glue the sorted lists together with the pivot in the middle. So I'll just put the pivot here so that we remember where it goes when we're done. So that's the first level of our tree. We've got our two recursive sets, I1 and I2. And we've got our pivot in the middle. And now, since this is a recursive call, we do the same thing here. We choose the first item to be the pivot. So the first item is 1. And the left list, and all the things greater than 1 to the right list. And the pivot in the middle. Again, our left list is called I1, and our right list is called I2, because this is recursion. So we reuse the same names. And now we have 2 lists of length 1 to sort, which means they're already sorted. So we're done down that level of the recursion tree. We still have to sort this array recursively. We choose the first item as the pivot, that's a 7. Items less than 5 go over here. Items less than 7 go over here. Items greater than 7 go over here. Put the pivot in the middle. And now we're done. It's just a matter of, as we go back up the recursion tree, we're going to glue all these little lists together back into one big list. And they just all come out in order. We're done. So any questions about that example? Yeah.
So you arbitrarily just chose the first one to be
For kicks, exactly.
and it just turned out to be the best possible way to use the example.
Because I deliberately arranged the example so that it would be the best possible thing for this example. Yeah. Absolutely. Yeah.
How random does this have to be for your quick search to run in like n squared time?
N squared? Well, it runs it most likely to run in n squared time if it's not very random at all. So that leads me to my second example. Thank you for the segue. Let's look at what happens actually if we try to use this version of Quicksort to sort a sorted array. Now, of course, the algorithm doesn't know that the array you're giving it is already sorted. It finds that out the hard way. But the numbers just happen to come in sorted order. But we don't know that, so we go ahead and try to sort them. So the first thing we do is we pick the first item in the list to be the pivot, and that's 0. And we put everything less than 0 into a list over here, and everything greater than 0 into a list over here. And we put 0, the pivot, in the middle between the 2 lists, although this middle is not looking very middle-ish. And that's the first level of our recursion. And now we do it again. Now, since our rule is pick the first pivot, the pivot to be the first item in the list, we pick 1 as our pivot, and now everything less than 1 goes into this list. Everything greater than 1 goes into this list. And the pivot goes in the middle between the 2 lists. And you can probably see where this is going by now. Go to the messy conclusion, but the point is, if you choose your pivots well, then you can get n log n time, because if you get lucky, then your recursion tree will have big O of log n levels, and just like in merge sort, at each level of the tree, you do big O of n work. Takes big O of n time to do all the partitioning at each level of the tree, and you're happy. But if you make a bad choice, and your pivots tend to be extreme, like the highest number or the lowest number, or something close to the highest or lowest number in the array, then you do a really bad job of partitioning. You get a really unbalanced recursion tree, and now you get n squared performance. So Quicksort can be fast, but it's also temperamental. You have to choose pivots a lot smarter than we just did. And it's pretty clear that when the input list is already sorted, choosing the first item as the pivot is a disastrous policy. So we're going to need a better pivot choosing strategy. largest key in the whole list. So if you're sorting an array of length 2, then obviously one of the lists is going to come out empty. So if I choose 5 as the pivot, then the list of items less than 5 is here, the list of items greater than 5 is here, and the pivot goes in the middle as usual. So there you go. Other questions? Hopefully we can do something smarter than just choosing the first item to be the pivot all the time. And actually, the smart thing turns out to be pretty simple. You roll the dice and you randomly choose a pivot out of all the keys in the list. This is a time-tested and well-respected method. And it's also one of the first examples we're going to see of what's called a randomized algorithm. An algorithm where you can use random numbers to actually improve the performance of an algorithm. And there are a lot of randomized algorithms in computer science. It's a really fascinating field. And it's kind of amazing that sometimes by rolling the dice you can get faster results than what you could do deterministically. Yeah. Okay, well if you choose the that's a good question. What happens if you choose a number in the middle of the array? If you choose a number in the middle of the array, I can give you what's called a pipe organ input, which looks something like this. I start small, I rise up, I hit my peak in the middle, and then I go back down. And if you use the always choose the middle item to be the pivot strategy, then this will run in n squared time. So any pivot strategy you give me where you don't roll a random number, I can probably figure out an array that will mess up your strategy. Yeah?
If you have some idea about what you suspect that the list will be, what it will look like, or the distribution, could you then choose a pivot based on that? Like, if you suspect that it might be kind of a pretty old pivot,
If you know something about your array, then yeah. If you have good information about what the distribution is, like if you have an array of random numbers and you know the distribution of the random number generator that generated those numbers, then yeah, you can pick a pivot based on what you know about the distribution and forget about actually looking at the numbers in the array to do that.
But
Sure.
if it's somewhat symmetric, then wouldn't it be good to choose something that's close to the mean?
That would be the first pivot. Well, but then of course you have to think about what the next pivots should be as well. Once you've chopped your bell curve in half, you have to know more about the distribution than just where the mean is. But yeah, I think that can be done. For sure. Mind you, if you're given an array that you know is already mostly sorted, you might just want to use the version of insertion sort I told you about, where the running time is proportional to the number of inversions in the list. Other questions? Okay. So randomness works. On average, you get a 1/4, 3/4 split. Sometimes you do worse than that, sometimes you do better than that. But if you get a 1/4, 3/4 split at least half the time, which you do, that's enough to prove that randomized quicksort runs an expected n log n time. And we'll do that in a lecture later this semester when I devote a whole lecture to randomized algorithms and how to analyze them. But for now, take my word for it. One thing, well, if you don't want to take my word for it, then you can go look at Goodrich and Tomasia section 11.2.1 and see the proof right now. So they've got a proof there for you if you're impatient. So they show that the average running time for those of you who've taken a probability class, when I say average running time, I really mean expected running time. Is in big O of n log n. We use random pivots. So that work well in theory, but it works well in practice as well. And pivots are good. They work. There's one more thing I should tell you about, which is there's an augmentation of that strategy, which works even better when you have a large enough list to justify it. Like say you have a list with 50 or more items left in it. Then you can use something called the median of 3 strategy. And what the median of 3 strategy does is, instead of just picking one random pivot, we choose 3 random pivots, bing, 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 and then we figure out which of those 3 is the middle of those 3. So just the median of those 3. Then we use that as the pivot. And again, you can apply probability theory to prove that this is even more likely to give you a good balance than choosing one random pivot. But in practice, it only pays off if you've got enough items, because it takes extra time. So what you want to do is, at the high levels of your recursion tree, when you've got lots of items to sort, use median of 3. And as you go down, then you're getting to smaller and smaller subsets, like you're sorting just like an array of 10 items. It doesn't pay off to do this anymore. It's too much time. Yeah?
Okay, median of 3 chooses 3 at random.
3 at random.
So it's still a random algorithm because
Yep.
that's a little less.
It's still a random algorithm. I wouldn't even say it's a little less random. Depending on how you define random, it's maybe a little more random. But the probability theory says it works faster. Yeah. All right, linked lists. So we have one other issue to resolve, which is when you have keys that are equal to the pivot, what do you do with them? The answer is going to be different for linked lists than it will be for arrays. And here's my answer for linked lists. Well, okay. Let's do a little thought experiment first. Suppose we put all items having the same key as the pivot into the first list. So think, can anyone tell me what is bad about this strategy? Let me ask this guy if he has the answer first.
It doesn't balance out the list well. It still happens that the list, if there are a lot of key items with the same key as the
Right, if there's a lot of items with the same key, this is going to suck. So anything less than or equal to the pivot would go into I1, is what this is saying. So yeah, here's the deal. Suppose that I've used this strategy, and now I sort this array. Now, once again, okay, here we have an array where all the keys are the same, but the program doesn't know that when it starts sorting. It just says, here's a bag of numbers, please sort them for me. So what does it do? Well, it picks a pivot, which is 5, and everything less than or equal to 5, other than the pivot, goes into list I1. And the pivot goes at the end. And you can see that what's going to happen here is exactly the same thing that happened here. We're going to get quadratic number of time. So this strategy is not going to work for either linked lists or arrays. We're going to come up with a better strategy, and it'll be different for linked lists and for arrays. The better solution for linked lists is pretty easy. It's to partition I into 3 lists instead of 2. I will call those lists I1, I2, and IV. IV key, obviously, is going to be the list of keys that are equal to the pivot. And actually, I had said earlier that the pivot itself, V, doesn't go into any list. But now that I've got this new list IV, we can put the pivot there as well. You might as well just throw everything whose key is the same as the pivot into this list, including the pivot itself. Now, once we've done that, we can recursively sort S1 and or I1 and I2 as usual. But there is no need to sort IV. All the keys are the same. And once we've recursively sorted I1 and I2, yielding lists S1 and S2 that are sorted, then we just concatenate the three lists together. So having done that, suppose I try to sort this array here with this strategy. I won't make it all the same key. I'll just make it mostly the same key. That's more interesting. At least sorting has something useful to do now. And in that case, suppose I choose the pivot to be 5. Then all the keys less than 5 go into this list. All of the keys equal to 5 go into the middle list. And all the keys greater than 5 go into this last list, which gets sorted recursively. And you can see that by pulling out all the items equal to the key and not sorting them, if you have lots of duplicates, that's really going to pay off in speed. You never have to touch that array again. Or that linked list, pardon me. Yeah.
So where does this scheme fail? Is there somewhere where it's like worse off than a different technique?
So for linked lists, this scheme as I've described it now is pretty good. The one thing you can say about it is that if you compare this versus merge sort always partitions lists perfectly, exactly a 50-50 split. Quicksort, it's a little bit off. It's like a 1/4, 3/4 split on average. And therefore, quicksort won't have quite as balanced a recursion tree. It's going to cost a little bit more, maybe a slightly bigger constant in the running time, usually. But it depends on how you implement it. If you code it, this way, maybe you'll get it running a little faster than merge sort. Who knows? Does that answer your question? Okay. I can't think of any other disadvantages to this right now. Yeah.
Are we talking about lister, or does it work equally as well for arrays?
So this does not work very well for arrays, and the reason why is if you want to do an in-place array sort, then the question is, where do you put these 5s? It's like, if you have lots and lots of memory and you can create new lists and new arrays, then it's no big deal. This works fine. But when you're sorting arrays, usually you want to do it in place. And quicksort is actually fantastic for in-place array sort, but not if you try to put all the keys that are equal to each other together. That's very messy. And I think it'll be clearer why when I show you the code for sorting arrays, which is our next topic. About this is that choosing a random pivot out of a linked list is a little bit annoying because you actually have to walk through the linked list to find it. With an array, choosing a pivot randomly is easy. Roll the dice, you get an index, you look in that array index. With a linked list, if you decide that the random pivot you want is the last item in the linked list, you have to walk through the list to find it. But if you don't do that, then you might get really unbalanced lists, so it's worth the extra effort. quicksort on arrays is where the real magic happens. Quicksort really shines for sorting arrays, as I've said, because the constant in the big O notation tends to be pretty small. And quicksort can also be done in place. And when it's done in place, it's fast. However, a fast in-place quicksort that's always fast and that works well in practice is pretty tricky to code. It's very easy to make bugs in the algorithm if you do it wrong. Goodrich and Thomasia did. Their quicksort on arrays, the one that's in the book, it runs in quadratic time on arrays where all the keys are the same. So they blew it. I'll try to do better. So here's what we got. There's an array, I will call it A, that I want to sort. And specifically, this is going to be a recursive algorithm. I want to be able to sort a subarray without creating a whole new array. So I'm going to have a couple of indices that I pass into the algorithm as well. So I'm going to say, okay, quicksort algorithm, I want you to sort all the region, the subset of this array, from A low to A high. Again, the purpose of this is to support recursive calls from quicksort to itself, so you can sort hard and low. Now, here's how it works. We choose our pivot V as usual. The first thing we want to do with an array, since we're trying to do things in place, it's a little complicated. The first thing we want to do is get the pivot kind of out of the way. And so what we do is we swap it with the last item in the array. And by last item, I really mean the last item in the subarray, which is A high. So now that we've got the pivot out of the way, all the other keys are contiguous, and we can sort them. All right, so let's look at what we got so far. Here's an array I want to sort, and I've chosen the pivot V. Low is the index of this item. High is the index of this item. This array may or may not go on further in each direction. But I want to sort this portion of the array. First thing I do is I swap V with high. So the pivot is now safely isolated at the end of the array. We can sort everything else. What I'm going to do is I'm going to create a pointer I, whose index is initially one less than the first index we want to sort, and a pointer j, whose index is initially one higher than the stuff we want to sort. So the idea is that at any time, the stuff that remains to be sorted is sandwiched between I and j. So here's the stuff we want to sort. It's between I and j, not counting I and j themselves. That's what we want to sort. Then, write this down. So initially, I is initially equal to low minus 1, and j is initially equal to high. And I and j sandwich the items to be sorted. What we're going to do is, as we go, we're going to enforce the following invariants at more or less all times, or at least at the end of each iteration of the outer loop. The invariants are, first of all items xi have a key that's less than or equal to the pivot, and all items to the right of index j have a key that's greater than or equal to the pivot. And that invariant is initially true because all the items are to the right of I and to the left of j. And then we're going to do this. We're going to, once we, from that point, we're going to do the following steps. We advance I until we reach a key that's greater than or equal to the pivot. And we're going to decrement j to a key that's less than or equal to the pivot. So, again, here's our array again. I starts here, moves to the right until we find a key that's greater than or equal to the pivot. And that key is 8. J starts here and moves to the right until it finds a key less than or equal to the pivot. And that would be this 4 here. So now I from the J and, I from the left and J from the right have now found 2 target keys that are on the wrong side of the partition. And we're going to get them both on the right side of the partition by swapping them. And then we're going to repeat this process, the last 2 steps, over and over again, until the 2 pointers, I and j, cross. So we advance again. And now I moves up to 9, j moves back to 0, and we're done partitioning this array because I and j have crossed. Now all we need to do is swap the pivot back to the middle. And the way we do that is we take whatever key is at I, and we swap it with the pivot, which is still here at the end of the array. So now we have everything up to j, well, everything up to I minus 1 is things less than or equal to the pivot. Pivot goes back in the middle, and everything after I is stuff greater than or equal to the pivot. Any questions about that? So what do we do with key is equal to the pivot? Well, what this rule says is that we stop at them and we swap keys equal to the pivot. And that might seem strange to you. Why do we swap a key that could go into either the left side or the right side equally well? Why not just leave it where it is? And the answer is, if we didn't do that, which is the mistake that Goodrich and Thomassia make, then if you had an array where everything is the same, then your I pointer immediately advances all the way to the end. Your J pointer never makes it backwards. And now you put all of the 5s into the left half of the recursion, and you get n squared running time. So that's what Goodrich and Thomasia did wrong. If you make I and j stop every time they hit a key that's equal to the pivot, then this is what happens. I advances 1 step, j moves back 1 step. They both stop, and you swap the 2 5s. I advances another step, j moves back another step, and you swap the 2 5s. I moves forward another step, j moves back another step. Now, so what we're doing is, if all the keys are the same, we're going through and we're swapping the 5s with 5s until we reach the middle. Now that may sound stupid, but the reason it's smart is because it partitions the array exactly in half. Yeah?
So if R is into a value that is if J runs into a value that is less than the pivot and gets into the greater values, you'll swap those.
Yes. But you'll still get a good partition. Yes?
Can you write that down? What you should swap the instead of the end or I and j?
Write down what?
Write down what you're swapping. Are you swapping the items at I and j?
That's right. You're always swapping the items at I and j. So when you first start out, I moves forward 1, j moves back 1, and these 2 5s get swapped. I, j, these 2 get swapped. This one doesn't get swapped itself, but that's where we stop. But if you had a big array, you'd have a nice symmetric pattern where everything gets swapped around the center. Yeah?
I and j is the same cell. How does it get partition?
If I and j end up at the same cell, like this, then the rule is always, at this point, you're going to partition the array around I. So at this point, you forget about j. It doesn't matter where j is. It only matters where I is. So I'm going to take whatever square I is at, and I'm going to move the pivot into that square. And whatever item was there gets swapped over here to replace the pivot. Other questions? Okay. Well, you have the code in front of you. It is worth studying this code. This code is really slick, and this code, well, although it's not very readable here, hopefully it's readable in front of you. There's handouts on the stage if anyone didn't get one. Looking at this code will give you some idea of why this is so fast. The main observation is that the reason it's so fast is because the inner loops are really simple and tight, and there is nothing unnecessary in there. And that's why the constant factor hidden in the big O n log n is small, is because there's very little happening on each iteration of the inner loops. And the inner loops actually are really, really short. These 2 things, these 2 lines, one that advances I and one that moves j back, those are the inner loops. Those are the things that you want to run the fastest, because those are what get executed n log n times. And they do their job really quickly. So let's start again from the top. Quicksort is the name. It takes an array A and array bounds low and high, as usual. And getting the base case is really easy. If low is less than high, then we don't do anything. That's the base case for the recursion. If low is greater than high, then there's at least 2 things in the array. So we sort them. We choose a random pivot. Here's the swap that swaps the pivot with the thing at the end of the array, so that all the array items are contiguous and we don't have to worry about the pivot getting in the way. Then we set the bounds as I said. The outer loop is the one that does 1 swap at most per outer loop and figures out when I and j have crossed. So So the loop says do something while I is less than j. As soon as I is greater than or equal to j, I and j have crossed, we stop. The inner loops are the real key here to the speed. The inner loop is just increment I as long as I is less than the pivot. That's all it does. Check if I is less than the pivot, increment. Check if I is less than the pivot, increment. Super fast. The other one is slightly more complicated. J minus minus. Do J minus minus while the thing that J is pointing at is greater than the pivot, and we need an extra conditional here just to make sure that J does not run off the end of the array. We didn't need that condition for I because there's always a pivot in the last place to keep I from running off the top end of the array. But we do need an extra conditional to keep J from running off the bottom end of the array into the negative numbers. And then, lastly, we swap unless I and J have already crossed. So one thing that people often ask is, why do we do this complicated thing where we're swapping 5s with 5s and more 5s with 5s just when all the numbers are the same? Why don't we check for that? Check if something is equal to the pivot and just stop and don't swap. The answer is, if you put an if statement inside one of those inner loops, it's going to be a lot slower. I mean, by a factor of 5 probably. If statements are slow. Right now, these loops are super fast. All I do is increment, test, increment, test. You do one extra test to see if you have a pivot equal to the key. You're going to slow down this code a lot. You want to do that. Any questions on this code? All right, well, I wish you all good luck.